We've already played with higher order derivatives when we were doing single variable calculus. Our plan here is to adapt the same techniques, but now to multivariable functions. Importantly, when we had a function of one variable, its derivative function was often also differentiable, so we could compute second, third, fourth derivatives, etc., etc. This same thing can happen with multivariable functions. When we take a partial derivative of an n-variable function, what's left over is also an n-variable function, which might be C1 itself. To see this, let's look at the function f of xy is x squared y to the 5. Differentiating with respect to x gives us 2xy to the 5, which is still a function of two variables. Just as the y derivative, 5x squared y to the 4, still depends on both x and y. Again, if these are also C1 functions, and for us they always will be, then we can again take their partial derivatives. Taking the x derivative of the x derivative gives us this, while the y derivative of the x derivative is as so. We can do exactly the same thing to the y derivative, computing its partials with respect to both x and y, and in that case we get the following. There's a lot happening here, so let's highlight some important points. There are a lot of second derivatives. In fact, I want you to take a second and see if you can determine how many second-order derivatives exist for a general n-variable function. Since we have n choices for the first variable that we differentiate, and n choices for the second variable, that leaves n squared second derivatives. Next up, we want a better notation system for tracking higher-order derivatives. In our simple notation, we'll just concatenate the variables to indicate which variables we differentiated. In the case of the xx derivative, we'll write it like this. Or in full Leibniz notation, like so. The yx partial is very similar, with the only major difference appearing in the full Leibniz notation, where we have this weird dx dy term in the denominator. And finally, we say that higher-order derivatives, which consist of differentiating the same variable over and over, well, we'll call those pure derivatives, with all other derivatives being called mixed derivatives for obvious reasons. And while this conversation focused on functions of two variables and the second-order derivative, everything here generalizes to n-variable functions and the kth order derivative. Now for a harder example, let's find all of the second-order derivatives of the function f of xy equals e to the x squared y. There are 4 such derivatives, and I'm going to do the 2 hardest examples in intricate detail. I'll give you the answer for the other 2, but I'm going to leave them to you to try and solve on your own. Now the first thing that we want to do is find the x derivative, for which we'll need a bit of the chain rule. Now that we have this, we can differentiate it with respect to x and y again. The xx derivative is the x derivative of the function above. And I'm going to be really careful here and try and write it so that my 2's don't look like partial derivatives. So we'll pull out that 2y term since it's constant and differentiate with the product rule. Again, note that I'm not reinventing the wheel. I know what the derivative of e to the x squared y is from above, so I'm going to use that to help me. Factoring out an e to the x squared y then gives us this. Now it's the same story for the yx derivative, where again we'll factor out the 2x term because it's constant in y. Another product rule and chain rule awaits us. And factoring e to the x squared y then gives us this. The other 2 derivatives are yours to check, but here are the results that I got. And there you have it. So higher order partial derivatives are computed just by differentiating the partial derivatives themselves, with the caveat that, well, there's a lot more of them.